Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD aerodynamic analysis of a drone using SolidWorks Flow Simulation. You can see the model. This is a very popular drone known as Reaper MQ9. It is widely used in US Army. It contains laser guided missiles, you can see here, and this is the camera, and this part is known as nose. This is the landing gear. This is very popular in US Army. The speed of this one is very high. It can run with a maximum speed of 275 miles per hour, or approximately you can say 135 meters per second. And some of the models can run approximately 34 hours continuously. The cost of this one is approximately $32 billion, right? Two different types of analysis can be done with this Reaper MQ9. At the back side, you can see one turbocharged propeller is there. In one analysis, we can use the turbocharged propellers that can run the Reaper, and another thing can be done, like considering the operating speed of this Reaper, we can start simulation. Right, so two different types of analysis can be done here, and here in this case we'll not go much deeper into this analysis. We'll try to find out aerodynamics. In this analysis, we'll find out different global goals like drag force, full force, and also we'll see the dynamics of flow particles, and we'll see different cut plots of pressure and temperature for different planes, and also we'll see the dynamics of flow particles. Right, so without wasting further time, let us start our simulation. Right, first of all, we need to start with the flow simulation here, and flow simulation environment will be created with the wizard itself. Default name of the project we are keeping as project 3. Next to that, as usual, we're considering SI system. Pressure we're considering megapascal, as high pressure will be generated, so we're considering megapascal as a pressure unit. As per normal practice, we're considering temperature as degrees Celsius. Next to that, it will be an external analysis, and from physical features it will be fluid flow, and we're considering gravity also. So you can see the direction of gravity is Z, right? Okay, so along Z it will be minus 9.81 meter per second square. And in this case, you can do two different types of analysis. We have already told that we can use the turbocharged propeller. In that case, you should consider this rotation also, but in this case we are not considering this rotation of the propeller. In this case, the operating velocity of the Reaper will be considered as the input velocity as a boundary condition, right? So we are not considering rotation. Next to that, from gases, it will be air as the default fluid, and we are considering humidity also. Next to that, default wall thermal conditions and roughness we are considering. Finally, from thermodynamic parameters, pressure will be 0.10135 megapascal and temperature will be 20.05 degrees centigrade as default temperature. Right, next one is very important parameter, is actually velocity parameters. You can see here the Reaper will be moving in x direction, so the velocity of air will be opposite to x, that is it will be minus, right? As I told, that operating velocity of this Reaper is actually 135 meters per second, so here in this case velocity of air will be minus 135 meter per second. We can provide that one here. In x direction it will be minus 135 meter per second, and humidity actually we are considering this one to be 60%, and coordinate system it will be along x, because the Reaper will be moving in x direction, so coordinate system we're considering as x. So with this one we can finish the setup, and you can see the computational domain. It is preparing model geometry. Next to that, we need to select some goals. You can see this is the computational domain. We have made the back part more to see the effect of this dynamics of flow particles, and we have selected several goals here. 4 different goals we have selected. All are actually global goals. First one is actually minimum total pressure. Next one is maximum total pressure, and third one is drag force, that is a force in x direction, and finally lift force, that is a force in z direction. So 4 different goals we have selected. And for meshing, let us see what we have done for meshing. A definition from display refinement level, you can see we have refined up to level 2. Okay, as you have run this one, so we can see the results from here. Results are not loaded, we can load it. Let us load the results. Now first of all, you see different cut plots of pressure and velocity from different planes, right? So let us insert cut plots. We'll see velocity from YZ plane, and the display pattern will contain contours, isolines, and also streamlines, right? Grand check. So let us play it. You see some vortex motion is created at different places. This is the front end, and that is the back end actually. So the velocity profile, you can see at 4 different places you can see vortex motions are created. Clear and hide this one, and we need to see pressure variation from this plane, right? Let us see this one, edit definition, and instead of velocity you see pressure distribution through the YZ plane. Let us see this one. This is pressure distribution. It will be better to see in the form of an animation, right? Let us play it. So we cannot see that much of variation in pressure, but it is clearly evident that some vortex motion is created at different locations. Let us clear and hide this one. Let us say velocity cut plots from front plane, and from display pattern we are considering contours, isolines, and streamlines. Isolines are the interface between different layers. So green check. This is the velocity distribution through front plane. Let us see this one in a different way. Let us view this one in the form of an animation, right? Let us play. Let us change the orientation. We can see it from different places, right? So cut plot 1, clear and hide, and we want to see from different places. Cut plot 1, edit definition, and we want to see from XZ plane, and again we'll see the different same thing like velocity distribution, and a display pattern will contain contours of velocity with isolines and streamlines. Go and check. You can see this one. The velocity profile, you can see it is widely spread at the back side, indicating light orange color, which means that velocity is in the range of 133 to 147 meters per second, right? Our operating velocity was actually 135 meter per second. So let us run this one. Let us clear and hide this one. Next to that, we see surface plots also. Insert surface plots, and we see pressure distribution on all surfaces. You see on all surfaces pressure variation is not that much. It is almost similar pressure, and the front side you can see little bit of higher pressure is there, indicated by little greenish yellow color at the front side, right? Throughout all other places pressure is almost constant. At some places only you can see pressure distribution is little different. Almost in all places pressure is equal. Here also you can see some different pressure is there, right? Clear and hide this one. Next to that, we want to see the most important part, that is our dynamics of flow particles or flow trajectories, right? Let us see that one. Let us play this one. Flow trajectories. Let us play. You can see the dynamics of flow particles is smooth, so we don't see that much of deviation from the flow particles. That indicates the design is perfect, and at some places only you can see different colors. That means velocity distribution at this location is actually little bit of less at the back side. In all other places you can see velocity distribution is almost equal. That means all the particles are having almost equal velocities. Flow trajectories, insert, and instead of 20 numbers we want to make it 200 numbers, and we're going to see static appearance, right? And it will be in the form of rectangle. Let us change it to pressure also. So pressure deviation, we cannot see that much of deviation in pressure, right? Now the most important part, that is our goal ports. We're going to see our results from goal ports, right? So let us clear and hide this one. And we want to see results from goal ports, right? So goal ports, insert, and we want to export all the results to Excel. So select all the goals and export to Excel. These are the results. You can see this is the data containing all the different parameters. First one is the lift force. You can see that after 94 numbers of iterations, lift force is actually 210 Newton. This is not that much, it is very less, right? It should be having high actually. Next one is actually drag force. Again, after 94 numbers of iterations, the drag force is also minus 170. This is good enough. So drag force should be as less as possible, right? And next one is maximum total pressure. You can see this one up to 94 numbers of iterations. Maximum total pressure is 0.1224 megapascal. And next one is minimum total pressure. That is also up to 94 numbers of iterations. It is 0.095 megapascal. This is very less, so the pressure difference is very high, right? Let us close this one. We can view all the results here itself also. Let us show it. These are the results obtained in a single place. We can view it in the form of graph also from here, summary, and let us see in the form of history. These are the same results what we saw in Excel, right? First one is actually minimum total pressure, second one is maximum total pressure, third one is drag force, and finally lift force, right? Let us close this one. This was a very simple analysis of a Reaper MQ9. This is a very popular drone in US Army, and we have undergone a very simple aerodynamic analysis of this Reaper, and in this analysis we saw the dynamics of flow particles, and also we have seen the different curve plots of velocity and pressure from different planes. And as a goal plot, we could see the maximum and minimum pressure developed, and also we could see the drag force and lift force as a global goals. Instead of stopping it here, we can do something else, like by providing the RPM of the turbocharged propellers as the initial boundary conditions, we can start another analysis and do the same things, right? So thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.